Hello, Thomas. You may begin.
Hi, good morning or good afternoon or good evening, and welcome to this webinar. We were just waiting for Thomas Mueller to join and introduce the webinar, but it looks like there's a technical problem preventing him from doing that. So I'll just go ahead and introduce the webinar and introduce myself as well. I'm Peter de Wolf. Welcome to all of you. I'll be talking to you about ultra-high resolution nanoelectrical measurements for semiconductor devices and applications today. I'll do the first part of this talk, and after introducing it, I will switch it over to Dr. Pierre Eben from IMEC, International Microelectronics Institute in Leuven, Belgium, where Pierre has been working for a number of years on advanced nanoelectrical characterization using AFM as well as some other methods. Pierre has also completed his PhD work here a number of years ago and is one of the world experts in this field right now. Myself, I'm the Director of Applications at Bruker, and I'm actually also an alumni from IMEC, having worked on similar topics here a long time ago now. So let's get started. The presentation, you can send in some questions on the chat box. Please feel free to do that. I'll be happy to answer those. If for some reason we cannot handle that in the time of this webinar, we'll make sure you get your answers afterwards by email, etc. The webinar will also be recorded, which is one of the reasons you're also muted as attendees. So you can also look it up later and re-listen to it if you liked it. So let's get started. All right. So nanoelectrical modes using AFM, there's actually a whole wide range of those modes. And this table on this sheet shows some of the electrical properties that one can measure and the corresponding AFM modes. Lots of acronyms on this slide, and I'll just point to some of those. And an AFM uses a sharp tip. So basically, anything we can use a macroscopic probe for, as we use on a handheld multimeter, for example, we basically can measure that with an AFM as well. There's usually a trick involved to get the right sensitivity when we work at nanometer scale, but it's very similar in concept. So some that I will point out are the one at the top for conductivity or resistivity measurements, which is basically the same thing. There's a number of modes: conductive AFM, tunneling AFM, scanning spreading resistance microscopy, all variants of the same theme, which is measuring currents or conductivity while applying a voltage. The difference in the modes is usually related to the linear amplifier that is used, or the current amplifier that is used, which can be linear or logarithmic and have different current ranges. And those will be chosen in function of the application, semiconductor or other type of materials. There's one variant of the mode which is called peak force tuner, which overcomes some of the limitations that the other modes have, as they are based on contact mode. Often in electrical measurements, we need a contact between the tip and the sample, and that's pretty good for electrical measurements, but not ideal from an AFM point of view, which can wear out the tip easily because of the lateral and the vertical forces, which could be higher than we wish for. Peak force tuner is a mode where we move from contact to an intermittent contact to overcome those limitations. But a second family I'll point out to are the maybe the surface potential and work function measurements. And I point this one out because it's also one of the most popular electrical modes. KPFM, or Kelvin probe force microscopy, is the commonly used mode there used to measure those properties. And again, there's an implementation using the peak force approach as well of that. And the third one I'll point out, as it's very relevant to semiconductor characterization of high-resolution devices, is the carrier densities. Very often we're interested in measuring carrier density in semiconductor devices. There's two methods that are commonly used: scanning capacitance microscopy and scanning spreading resistance microscopy. We'll show some examples of all of these modes in the next few slides, as well as in Pierre's presentation. So a few examples of the conductivity or resistivity measurements here. Three different types of examples. And the one at the top left is a cross-section device, actually multiple devices. There's a couple of MOS transistor devices here cross-section. And in the current map, or the resistivity map, we can observe the gates, the source and drain implants, as well as some more details on how far those source and drain implants extend in depth or laterally, as well as a silici that shows a higher conductivity, a brighter image, a brighter color in this particular image. These particular transistors are of a 45 nanometer technology, a little bit older technology, but still quite relevant and illustrating what sort of a standard type of resolution as one can get with this method. The image below that shows a bunch of nanotubes, carbon nanotubes, that are positioned on the dielectric substrate. The carbon nanotubes are showing up as brighter because they are conductive, and while the substrate is not. Towards the top of the image, the nanotubes are higher conductive than towards the bottom. The reason for that is that these nanowires need to be electrically connected to the substrate, and they are connected electrically through a larger gold contact that is not shown in this image, but basically located just above the image. So we can see that the conductivity is higher when the nanotube is closer to that metal contact compared to further away. And we can actually extract from images like this the conductivity of each individual nanotube as we follow it. The current levels in this image are quite low. The scale is here a 4 picoamp scale, which is the difference between the brightest and the darkest area. But currents easily go to below 100 femtoamps. So this points to the need of electronics that can detect that low level of current. The third image on the right is an example of the peak force tuna mode. In this sample, which is a polymer blend of two components, polypropylene and EPDM rubber, the sample is quite a bit softer and more fragile than the other samples shown here. To image in contact mode is not trivial. So imaging in a non-contact mode or an oscillating intermittent contact mode like peak force tapping is a lot easier. That's what's happening here. The height image and the current image are collected at the same time, and the current is collected while that tip is having that intermittent contact. The spots we see are showing carbon black nanoparticles that are embedded into that polymer blend. One of the nice things of this particular mode is also that we can extract mechanical properties at the same time. In this particular case, the modulus and adhesion is shown, and the modulus map, for example, shows the EPDM rubber, which is a lot softer, darker in this image than the polypropylene matrix that it's in. So we can nicely correlate electrical and mechanical information, something that is more and more of interest, not only on polymers, but on a variety of materials. A couple more examples on these other modes that I pointed to earlier. The top example is a KPFM example on an active device. The device is made out of a nanowire, an indium phosphide nanowire positioned on two metal contacts, and a voltage is applied between the two contacts, about 3 volts. That makes it an active device. The KPFM method can be used to map how the potential distributes on that particular device. You can then look at details, how the potential drop is between the metal and the nanowire, for example, or at defects that might be embedded in the nanowire. It's a typical application for this KPFM mode. Another typical application would be to measure work functions for example, in multiple metals. The bottom image is a scanning capacitance example, and there's 3 images. One is topography, 2 are capacitance data. Again, on a cross-section device, so topography doesn't show much because it's polished or cleaved typically, but the electrical data show clearly implant regions. There's an N+, and a highly doped N region, a P-doped region, and then a low-doped N-type substrate. This is a silicon carbide double diffused MOSFET device structure. So we have 2 junctions in there. And in the phase image, the DC-DV phase image, so this is the first capacitance image, we can see where those N-type and P-type regions are exactly located. And often of interest is to find out what is that exact junction profile in there. In the DC-DV amplitude image, which is acquired at the same time, we can get a signal that is related to the carrier concentration. A higher carrier concentration results in a lower capacitance amplitude, and a low concentration results in a high amplitude. So based on that image, we can get an estimate of what carrier densities there are, what the carrier profiles are in depth or laterally, at least in a qualitative manner, and in some cases also in a quantitative manner. Resolution of the mode is typically limited by the tips and on the order of tens of nanometers. So after these examples, a couple of practical aspects. One practical aspect important for any AFM mode is the probe. This is really what enables high resolution. For electrical AFM modes, in addition to the tip sharpness, another property that is important is the conductivity and the hardness, or the wear resistance, because the tip will be in contact with the sample quite often in most of these modes. The typical probes that are used are metal-coated probes. I didn't show a picture of those here. Those are the standard probes. I show some pictures of a bit more advanced or optimized probes. First one is a platinum silicide covered probe. Platinum silicide is also nicely conductive, of course, but at the same time it's also very hard and very sharp. It basically maintains the sharpness of a silicon tip. Today, that's probably my preferred or recommended probe for modes like scanning capacitance microscopy. Second probe is a solid metal probe. Advantage of that type of probe is that when you wear out the tip a little bit, you still have the same metal and pretty much the same electrical performance, which can be nice, and we cannot have that with metal-coated probes. The third one is a diamond-coated probe, where the metal coating is replaced with a diamond coating. It's doped diamond so that it's conductive. Obviously pretty hard and nicely wear resistant. Conductivity is lower, but it's sufficiently high for most of the electrical modes. The coating is typically made up out of grains, which have a size on the order of 100 nanometer. And you do need a little bit of luck. There is a variation from tip to tip. Some tips are better than others, depending on the orientation of that final grain at the apex. A nice alternative, and actually developed here at IMEC, is the one at the bottom, is a solid diamond probe, a similar coating process, but now the full tip is actually made out of diamond. And the resulting tip on this can actually be extremely sharp, as shown by the TEM picture, where we see only a few nanometers of radius on that tip. For some of the highest resolution electrical measurements, as Pierre will surely show later here, this is the type of tip that is being recommended or used. A second practical aspect is the environment. A lot of the samples that we try to study, or their electrical properties, are actually influenced by the environment, and in particular by the oxygen and water content that could be present in the environment. At ambient conditions, we obviously have to face and deal with oxygen and water, and that thin layer can also can change the properties, but also reduce the spatial resolution. And the image shows an example. It's an example on ITO, transparent conductive oxide, topography on the left, and then 2 current images, one collected ambient conditions and one in a controlled environment. And we can see from the images there's differences, which we can also see from the histogram. The histogram on the right image is more rich. It's wider. It shows current over a larger range, and as well it shows two peaks. There's more information in there. Basically, it's seeing things that we could not see while staying in ambient condition. A third reason to be worried about the environment could be that when water is present and we start applying voltages, which is common when we do electrical measurements, we can start to form an anodic oxidation process, which will basically grow an oxide on the sample. It's very well known from nanoelithography experiments. That process could actually alter and change the electrical measurements in situ, obviously something we don't want. One solution to overcome that is to put your AFM in a controlled environment. One solution is shown here. It's a glove box that allows to go down to well below 1 ppm levels of oxygen and water. When doing that, we need to be careful because most glove boxes are not designed for AFM performance in terms of noise, for example. So we need to be careful about those aspects as well. We have seen improvements in doing that, and we've seen further improvements when we look at the empty chamber, so the small chamber on the right side that is used to bring in tips and samples. When we add to that empty chamber a vacuum pump, so when bringing in tips and samples and going through a vacuum cycle, we can further improve the measurement capability for the electrical measurements, at least for the AFM. The AFM shown here is the dimension icon, which is our standard platform for many of these electrical measurements that we will show. One example on a pretty nice sample, I think, developed here at IMEC is a sandwich sample. There's a very thin oxide that is sandwiched between two highly doped silicon areas. And the oxide is 3 to 5 angstroms thick only. So you need a pretty high resolution to detect that electrically. And if we do that measurement in ambient conditions, it's very hard or mostly impossible to detect that peak in resistance. Well, when we move it to the glove box, we can more routinely measure that peak, a nice proof of improved resolution or detection sensitivity. So moving back to the topic of the webinar, which is focused on semiconductor devices, there's a couple of pictures shown here that show the evolution of semiconductor devices over roughly 10 years, which is obviously hard to do in 4 images only, but it gives an idea of where the dimensions came from 90 nanometer about 10 years ago and what they are today. It's not only the dimensions, which has shrunk to tens of nanometers and sometimes less, it's also the shape of the structures have drastically changed. It's no longer 2-dimensional, it's now 3-dimensional. We have more complicated structures in FinFETs and TFETs. There's also lots of different materials from the classic silicon only. We now have silicon germanium, compound semiconductors, etc. All these things can complicate and do complicate the metrology. And if we look at the ITRS roadmap, the International Technology Roadmap for Semiconductors, that's reflected in those roadmap numbers or targets for the metrology. Spatial resolution of 1 nanometer concentration, so carrier concentration of 2% precision, and a range of 10 to the 14 to 10 to the 21. Challenging numbers. Classic methods have run out of steam. They don't have the resolution or the sensitivity or the combination of both to do this measurement. So more and more people are turning towards AFM to see how AFM can solve this challenge. This is a good point for me to hand it over to Dr. Pierre Eben, who will go into more details on this in his part of the presentation. So bear with me while I swap presentations here.
So good morning, afternoon, or evening to everyone. Just take a few seconds to switch the PowerPoint, I guess. Maybe go up. Okay. So yes, I will present you a few of the results that we obtained here in the team. As you can see, there are a few names here. Means this is a collective work that has been done on this. Okay, first, where we are speaking from. We speak from IMEC. IMEC was founded about 30 years ago. There were 70 people when we started. Not me, but when it was established here. And now IMEC is about 2,000 people. 400 of them are residents from companies which are partners of IMEC, and there are about 300 PhD students. As you can see, this is a mix in between fundamental research on like university research would be done, but also a lot of interaction with companies, as you can see also from the revenues. And this is also a nice facility. We have 2 clean rooms and a lot of different labs, as you can see on this image. So the mission is of IMEC, I said it already a bit, it's to perform world-leading research in nanoelectronics. This is innovative research, but this is with industry relevance. We try to be something like a missing block between R&D departments of private companies and research laboratories in universities. So this is a unique environment where we have facilities, people, and a broad variety of partners on the same site. What kind of research we do? It's very often multidisciplinary, but basically it is divided in different research programs. Division is made based on kinds of applications. You can see here I've listed 5 of the main important ones, and also based on the driving technology. And within IMEC, we have different departments. One of them is the one for material and component analysis. Within this department, there is the SPM team. As you can see, this department is composed of 5 teams, and also one spin-in named CAMS, which is basically making commercial use of the AFM research that we have done here, be it AFM service or the diamond probes that were mentioned by Peter, or dedicated test structures that were shown also. That's the team I'm leading, this SPM team, and basically we are doing relatively broad variety of different research. I will partially cover some of them during this talk. So it's SPM in the nanoelectronic field, to make it general. We work on TCAD calibration, development of new electrical AFM modes, tomography, 3D AFM, I will show a few slides on that. Conductive AFM on memory device, STM and non-conductive AFM in UHV 435. So quite broad range of activity. But our central research field in this team has been linked to one of these techniques in particular that we have invented here on site, and that we have also developed since more than 15 years now, which is the scanning spreading resistance microscopy. So most of my talk will be focusing on this technique, even if I will show you also a few results with different ones. So what is this technique is the first question. This basically SSRM. It's an AFM equipped with a conductive tip and with a logarithmic amplifier. And we put this tip in intimate contact with the sample that we want to measure. I will explain what kind of samples and how we prepare them later on. And we raster the tip, and for every position of the tip, we are measuring the current that is flowing from the tip, to a back contact. So measuring a current for a certain bias voltage applied between probe and back contact is actually measuring a resistance. The total resistance, if you see the setup that is described here above, is actually the resistance of the probe, resistance of the constriction, which is called spreading resistance, resistance of the sample, resistance of the back contact. But what we plan to do, what we want to do, what we try to do, is to be in conditions where the spreading the resistance is dominating over all other components, meaning having conductive tip, good back contacts, but also meaning having small size contacts. As you can see, in a simple contact, ohmic contact mode for a circular contact, the spreading resistance is equal to the resistivity of the material divided by 4 times the size of this constriction, of this electrical radius. So if we are able to get a radius in the range of 1 nanometer, for instance, then we have a spreading resistance which is quite large and which is dominating all the other components. So if the total resistance that we measure is dominated by this spreading resistance, then we have a direct measure for the resistivity of the material just below the tip. And knowing the resistivity, then we also know the active dopant concentration, be it electron or holes. To do that, we use tips as the one that you see here, which are diamond-coated tips. Why do we use diamond-coated tips? Actually, to make a good measurement, to have a spreading measurement and not a tunneling through any potential bias that may be present, we need to have a force which is high enough. In the following graph, you can see that the range of the force that we use for SSRM is typically in the range of the micronewton. That's the force you need to have the total resistance that you measure going down very quickly. So we have a technique which is used at high force, and therefore we need dedicated tips. The tips that you see in the small movie here is a diamond-coated tips. There are actually two technologies, as Peter mentioned, these diamond-coated tips and also full diamond tips that we developed here at IMEC. In both cases, the tips, they are ending with small or larger nano protrusions at the tip apex, meaning that the radius of the curvature of the tip seen from a large zoom view, let's say, it's not microscopic view, but not if you really zoom to the nanometer scale, actually is much broader than the actual contact size. You make the contact ideally with one of these nano grain at the end of the tip. But of course, you can make a contact with one, but you can also have multiple contacts. Therefore, we really want to work on having the sharpest tips that we can have. And that's the reason why we are preferring currently, most of the time, the full diamond tips. First reason is that they are lower aspect ratio tips compared to the CDT. I will show you once again a small movie here on the top. This is with high aspect ratio tip. What's happening if you come close to an edge, you go slightly over it, it's that you break your tip, what you don't want to do, of course. So that's the first reason why we use these full diamond tips. They are lower aspect ratio, so they do not suffer from the same kind of breakage. The second one is that, it was mentioned already, they are sharper at the tip apex. This is not a coating of diamond on top of an existing tip. It is really a mold that we do, which is very sharp. And then we fill this mold with diamond. So the diamond that we use to make the contact is actually the first diamond that has been deposited, which is composed of much smaller grains. So we are able to get smaller grains, and hopefully if we can make the contact with one of these grains, we are able to get very high resolution. Now a few words about this resolution that we can get. It's a bit counterintuitive that you have a technique which is very high force, and that in the meantime, I will show that later on, can deliver very high spatial resolution. So a few words about what's happening actually in the case of a contact between such a diamond tip and a piece of silicon. What I show here is true for silicon. It is not true for all semiconductor, but silicon is still an important one that we measure a lot. And basically for some of the other semiconductor, it is quite similar what we can see. Not for all of them. This is basically the image that you see here. This is a zoom view of the TEM apex of the tip. And you see that this grain here, that is the one that will make contact, is presenting a diameter, a radius of 2 nanometers, diameter of about 4 nanometers. And what we have done together with some colleagues from University of Sydney was to make some molecular dynamic simulation of the transformation of the diamond cubic silicon that we have in this normal phase, which is also called silicon 1, this the relaxed silicon. What's happening when we start to indent and to go to the kind of force that we are applying, and so to the kind of pressure in the range of 1 to 10 gigapascal that we indeed have below this very sharp tip indenter. And actually what we are doing is that we are making a phase transformation, starting from the diamond cubic silicon, which is having localized sp3 molecular orbitals, when we go into this high pressure, we generate a new phase, which is called silicon 2 or beta-tin silicon, which is a phase where every silicon atom is no more having 4 neighbors, but 6 neighbors, and where the sp3 molecular orbitals are actually replaced by sp3d2 molecular orbitals, in which d2 is corresponding to non-localized electrons, meaning that we are so generating a new phase of silicon, which is a metallic-like phase. And also in the meantime, we generate a volume reduction. And through the simulations, we have also been able to show that the drop of the resistance on the top graph, this is the pink curve, that the drop of the resistance is actually occurring at the same force that we also have this generation of beta-tin of silicon 2. So basically what we do when we use this high pressure is that we are very locally generate something like a small droplet of conductive material just below the tip. And this droplet can be as small as 1 nanometer. And that is, and most of the current that you're going to measure is going to flow through this droplet. Also through simulations, that's the bottom graph, we were able to show that the indentation that we generate after we remove the indenter is similar in experimental conditions and simulations. So that was a way to confirm that the molecular dynamic simulations that we had done were nicely corresponding with the experimental situation. That's how SSRM works. Now, first we were doing SSRM in air, in ambient conditions. And in Belgium that means sometimes also with a large humidity level. And we were encountering some problems. What we were encountering was multiple contacts. I told it already, we may have multiple grains doing the contacts. The tip breakage I was mentioning. The fact that we were not always, even with the full diamond tips, be able to reach the high resolution, even if they were better than the coated diamond tips. The fact that the image were degrading. You see here first scan and an 8th scan. You see that the image degrades scan after scan. And the fact that the noise level inside these measurements was not ideal. So here you can see the ITRS requirement, as Peter has shown already, versus the kinds of resolution and noise level. So precision in quantification that we could reach with the SSRM in air. So one of the ideas has been to try to look for better conditions to make these measurements. And when we might want to make an intimate contact between a small indenter and a piece of semiconductor, in this case silicon, it is of course very crucial that we can make an intimate contact, that there is no organic contaminant or water layer in between the sample and the tip. And that's what we could see also from simulations. Here you could see the simulation in the case of a water layer being present and in the case where there is no water layer. And you can see that the formation of these 6 coordinates phase, which is the beta-tin, metallic-like I was speaking about, is slightly retarded in the case that you have water. This is the blue curve. You see that the tail of this blue curve is happening slightly lower than the one of the pink one, which is the case where there is no water. So in air, when there is water, you need to push more to generate this small plastic deformation, and so to have the nice current flowing. And the second conclusion also was that when you are in the case of water being present, when you make an indentation and release up to the same force, you notice that at the end you have a plastically deformed pocket in the case of water being present that is larger. Means also that for the same kind of force that we apply, when we reach the force which is enough to generate plastic deformation, we deform a broader area. We are not able to indent so locally, to generate pressure so locally, and we are not able to generate so this plastic deformation as small as we can do in vacuum. So that's the point. Try to reduce the impact of humidity. I told it, one solution is vacuum. The other one is to use a tool inside a low humidity chamber. That's currently our favorite solution, because then you can take advantage of all the quality of the kind of AFM that you can put inside your glove box. Here again I show this graph where you compare the ITRS requirements with SSRM performance, and you can see that in the case of the Icon glove box we have been able to increase the resolution and to reduce the noise level. Resolution, Peter showed it already. We are able to measure in ideal conditions features which are smaller than 1 nanometer. And the noise level, this is measured here in this graph that you can see here, this is the average repeatability. You can see that air versus this icon glove box, there is a big improvement. If you would go to UHV, you can even go a bit further in terms of quality of the image that you can reach. But then, of course, you have all the complexity linked to the use of UHV. So at the end, doing this, you have a technique that's allowing you to get a very nice 2D profiling of carrier distribution. This is an example here for a slightly broad implant where you could compare the SIMS measurement with SSRM measurement. SSRM is in green, and you can see, for instance, that with SSRM we measure really the carrier, the active carrier. So the boron concentration that you have in SIMS, where you have this tail at the start going up to 10 to the 21 atoms, we can see that actually these dopants, they are not activated. That's why we use this technique. Very important to make SSRM is to be able to make a good sample preparation. You can measure, of course, on top surface of materials, but most of the time what people are interested in is that you make a cross-section and you look at the cross-section through one device. So that's one first important aspect, to make a cross-section. If you don't want to kill your tip, I show it, it's important to try to protect the place where your sample, where your device is typically at the top surface of your tip, so when you cross-section close to the edge. So we use silicon oxide, we also use silicon or a glass dummy that we glue on top of the sample of interest. You need to collect this current that is flowing from the tip to a back contact. Back contact, you can all make them manually, that's the classical way. But when you have short device, what we do more and more, measuring on real short device, then you replace this manual back contact by the use of FIP, focus ion beam. This is what is shown on the right-hand side image. You can generate a trench that you fill it with platinum, with FIP, very close to the structure of interest, down to 1 micron, and collect the current through this trench and then through a metal layer that you deposit on top of your surface. I told it cross-sectioning is a crucial aspect. One way to cross-section is polishing. That's, let's say, the historical way we were doing it. And we can reach roughness in the range of 0.6 nanometer or even smaller. We use still when we have very complex crystal orientation or very specific structure, but as soon as we can now, we prefer to use micro cleavage. We have a dedicated tool to do that, because we can very accurately position this cleavage down to 300 nanometers, and because this is even further reducing the defects and improving the RMS that we can reach roughness below 0.4 nanometer. And in some very specific case also, we want to have a cross-section position extremely accurately down to 10 nanometers. And then what we do, it's a new procedure we have developed, is to use gallium FIP, not to dig a hole, but this time to make lapping, to come with a very small angle of incidence and very small energy, and to remove a few hundred of nanometer at max down to the cross-section area that we want to reach. FIP, we use it also to mark the area of interest or to generate local back contact paths. So now we know about how we prepare. Let's go to a few examples. One first work that we are doing here is to try to use SSRM to help the calibration of TCAD. TCAD, basically, this is the whole package of simulation which is used to try to save costs in semiconductor industry in order to predict what different processing steps will give, and afterwards also to predict, this is process simulations, and afterwards also to predict the electrical properties of the device that are processed. And of course, these simulations, they need good models inside of them, that's the first point, but also they need to be calibrated. For years they were calibrated with 1D techniques, but it's like for the rest, these techniques, they run out of steam. So there is a need, there is an interest to try to make 2D calibration of this. So what we have been doing, what we are working on, is what you can see here. First, we make an SSRM image. You see on the right-hand side of this image here an SSRM resistance map. I'm just spreading resistance. On the left-hand side, you can see the good correspondence with TM. And then we quantify this SSRM. That's what you could see in this graph. On the right-hand side, you see the SSRM quantified. On the left-hand side, you can see a simulation. And then we can compare the map that we obtain with SSRM with the map that we obtain with a classical process simulator. And then what we can do also is to take the SSRM map and to plug it inside a device simulator so that we can simulate the electrical properties that would come out of a profile like the one given by SSRM. That's what you can see in this graph here on the right-hand side. You see in black the real, there are two electrical properties of transistors, that have been shown here. There is one which is called DIBL, drain-induced bias lowering, which is basically the lowering of the voltage you need to open your channel when you go to very small gate sizes. The other one is the VT as a function of the gate length. Just in black you see the real meshed characteristics on the device. And then you can see how we have been able to calibrate the simulation based on the SSRM indication. So we fine-tune the process simulation to have lateral under diffusion, pockets diffusion, depth of the source and drain that are corresponding to SSRM map. And when we do that, we see that we are able indeed to put our simulated device properties closer to the experimental measure ones. That's the first field of activity where we are very active, because being able to calibrate the process simulator is of course saving a lot of money for the semiconductor industry. We also do a lot of measurements for various clients via the spin-in structure that we have here at IMEC. I mentioned it in my introduction. This is one of the examples that we can show you due to courtesy of, thanks to courtesy of these spin-in cams. This is an example of a CMOS image sensor, and what you can see directly is that we can get a very high resolution 2D current distribution inside the individual pixels of a CMOS image sensor here. You can see on the left side the SEM, on the right hand side the SSRM image. From the same source, this is a DRAM here. You can see trenches, DRAM trenches, and you can nicely see in the SSRM image the implant out diffusion at the top and at the bottom of these DRAM trenches. One, I think, last examples from CAMs. Here it is power MOSFET. And here you can see, for instance, the dopant concentration inside an integrated Schottky diode in a power MOSFET device. As Peter mentioned, evolution is also going from classical planar structure towards new architecture. One of these architecture that is really already used quite a lot nowadays, but which is really a growing field of research and of production, is FinFETs. Basically, FinFETs are used to reduce all leakage current inside a structure. They are also used because inside FinFETs we can process new semiconductor materials. And one of the field of research which is very important nowadays is to try to have semiconductor materials that are offering larger mobility. And 3.5, in particular InGaAs, which is presented here, are materials which are offering very large carrier mobility in comparison with silicon. But of course, growing such layers inside these trenches is not, inside these fins, sorry, is not an easy task. And one of the problems that we may encounter is that some of the atoms that we grow may move when we try to activate these structures. And here what we have been able to evidence, it's what you see, for instance, here in this sort of banana-shaped red area, is the fact that you may have some phosphorus coming here from an indium phosphide layer, which is diffusing towards the silicon. In this case, we grow indium phosphide on top of silicon and then indium gallium arsenide on top of this indium phosphide. And this, what we have been able to show is that this was the first trial when we processed this structure, and it was not yet optimized, is that there was some phosphorus from the indium phosphide that was entering inside the silicon where it was acting like a dopant. And of course, these kind of features you can only see if you have a 2D structure. And also, I encourage you to look at the dimensions. You can see that we speak also about very small dimensions. The indium gallium arsenide layer, for instance, is smaller than 30 nanometer in depth. We use 3.5. We also use germanium, which is also a high mobility material. Same concepts. these germanium are grown on top of silicon, and also silicon germanium is used in this case. So you have silicon, then silicon germanium, and then germanium on top. Also for the reason that the lattice size of these different materials is different, so we use typically some materials which have lattice dimensions in between the one of the bottom material, silicon in this case, and the desired material that you want to grow, in this case germanium. So we were able to measure it, that's what you can see on the left hand side, and also we were able to identify, you see here these very small red spots on top of the fins. We were able to identify the presence of high phosphorus concentration inside the germanium, high conductivity inside this germanium, which is what we want to have actually. We want to have a very conductive material. FinFETs, and then even more localized and 3D structure TFET inside nanowires. There's basically vertical TFET, tunneling field effect transistors inside nanowires is also a very important and growing field. And you can see here we were able to image such a nanowire and also to make sections inside it and to make studies about, for instance, the change of the profiles at the center or at the outer shell of these circular cylindrical nanowires. And you could see the comparison with TEM once again. Okay, you see we go from 2D structure towards 3D structure. So it's nice to be able to cut and to have planes in the center, for instance, of a nanowire. It's even better if you would be able to see a 3D view of this, to be able to make a 3D SSRM mapping to make tomography. There are actually two ways to do it. One way is to use a dedicated test structure, staggered test structure. I will show you an example just later on. The second one is to make use of the fact that we use diamond tips. In theory, diamond should last forever, means you can use it not only to measure, but also to dig into the material, to remove some materials. It's what you can see here. We use, we make scans here. With decreasing the scan size, you can see you can generate something like a pyramid inside your material. Each scan, you remove a few nanometers of material, and then you can measure at different depth. So this we call slice and view. We use the same tip to slice, to remove some nanometers of materials, and then to make a measurement of the profile at a certain depth. Both concepts have pros and contras. I will not go into too much detail. I will just show you a few examples of this. The first one is going back to these nanowires. We had here a sort of a forest of nanowires with the staggering. So by making one section, we were able to see nanowires at different positions, and we can measure all of them. So it's what you can see here. And then we can reconstruct a 3D image of these nanowires. So we can really have a 3D distribution of the kairos inside the nanowire. That's the first example. Second example, it is CNT-based interconnects. Interconnect is the way to interconnect transistors in between them. It's very important, of course, and we want to have very small interconnects and also very conductive interconnects. So we are looking for alternatives to the current materials which are used to make interconnects, and one of these potential alternatives is to use CNTs. So what is tried here at IMEC is we make vias, we start to grow CNTs inside these vias, and then to fill them with silicon oxide. What we have been doing is to measure such a structure with these vias, and also to go layer by layer. And that's what you're going to see in the small movie here on the right-hand side. You see the SSRM map that we have acquired at different depths. And doing that, you will see that just afterwards. We can also reconstruct the image, and we can see that some of these nanowires, for instance, they can merge. I guess you can see this in this image. Maybe it was a bit too fast. I leave it for a second time. But you will see some of these nanowires, they can merge against each other. So we were able to get an in-depth about these nanowires. I really recommend to go to the paper of Andreas Schulz on this, because of course there is much more that we can learn from this image. So there is the reference here that I recommend you to have a look at this work. Okay, next idea. Same concepts. We really we make slice removal, but we want to make it in much smaller structure. In this case, this is a FinFET structure where the fin size is less than 10 nanometers at its top size. Mean we want to come very close to it, This we use focus ion beam to prepare a cross-section very close to the fin. And then we want to remove maximum 2-3 nanometers every scan, so that we can have at least one of these planes. This is the one which is shown in green here, which is in the center part of the fin. And that's what we have done here, and we were able, that's what you see on the map here in the bottom part, we were able to see, for instance in this case, which was once again the non-optimized process, that actually the plugs were not centered, so that as a consequence we had the possibility on some of the devices, not all of them, that the gate was touching one of these two wires. And also, due to the asymmetry, the drain was not implanted as expected, and there could be some leakage possible between the drain implant and the well implant. And if you can make these planes to go up to a certain level, also at the end you can reconstruct the full image with all these different planes all together. That's what you're going to see in the small movie here. You see we enter inside one of the fins here, you see the image. Now we go the other one, you will see we are in between two fins. So we leave the first fin and we come back to this fin, and then you can see we can make it transparent, the oxide part. We can rotate this, and you will see the interspacing between two fins. So we really start to have not only a 2D view, but the real 3D tomogram of the structure that we want to study, which is delivering some extra information. In this case, only one of the two source and drain, only the drain in this case was properly connected to the connector. Okay, one last 3D example. This is no more a classical SSRM. In this time we use conductive AFM. So basically we use linear amplifier, and also we really in this case try to reduce the removal rate. On this example that you're going to see here, in between the two different planes that we have, you have 0.7 nanometer, meaning that you are really speaking about very small removal rate every scan. This technique was used to, it's the work of Umberto Celano here at IMEC. I also recommend to go to his paper. You will have the reference just a bit later on the slide. This work is to study new kinds of memories, which are called CB-RAM, resistive RAM, that we try to develop here at IMEC and at a lot of different places. And so one of the critical aspects here is to try to understand all these conductive parts, which are the central aspect of these memories, how they are generated and how they can be removed. How these conductive filaments can be generated and how they can be removed. And what we do is that we are using an AFM tip first to generate them, and then we also use an AFM tip to scan at different depth inside these very thin layers and to see the shape of these filaments that we have generated. So that's what I'm going to try to show you in this movie here. You see here, we see a different depth. This is the central small spot that we should concentrate on. And you see the evolution. You have a 3D view of the same thing in the central part of this spot, which is on the right-hand side here of this graph. And we were able to for the first time, to identify the shape of these filaments that we are generating in these new kinds of memories. So I recommend that you go, if you are interested in this field, on the work to have a look at the work on Umberto Celano. And one last example, we are working a lot. I've shown a lot up to now. I've shown only up to now examples of measurements on inorganic materials. Of course, organic is also a very important growing field. And on organic also we are doing conductive AFM, meaning also at lower forces compared to what we do with SSRM. This is an example of organic materials which are used to make solar cells. This basically it's two material compounds here. And what is very important to understand is that all these two materials can be intermixed. With light entering inside these materials, we are able to generate some excitants. But then the big question afterwards is, are we able to have the electron and holes flowing through two of these materials, one to the anodes, the other one to the cathode? So are we able at the end to generate some currents? Don't we have a recombination of these generated excitants? And this is very crucially depending on the intermixing of these two materials at the nanometer scale. The only way to look at that is to be able to have indeed a cartography at the nanometer scale of this intermixing between the two materials, and also to have it at different depths. And what we have done on these very, very soft materials to be at different depths is that we have been using an argon cluster beam to dig holes at different depths. That's what is shown on the right-hand side of this image. And afterwards, we make a CFM image at these different depths inside it. And then we are also, this is what you see here on the right-hand side, this is the kind of image that you can get at these different depths. And then we are able to identify the two materials. We are able to identify, in this case it is P3HT and PCBM. We are able to identify, based on the fact that they conduct or not, which material is PCBM, which material is P3HT. And we are able to do that at different depths. And what we have been doing in this case was to study the aging. For organic materials, one of the very crucial aspects is that these materials, they degrade, they age extremely fast. And that's what you can see in the graph on the left-hand side here. You can see that with time, the materials are aging, and therefore there is not anymore a good intermix between the two materials, and therefore the excitant which are generated, they will recombine much more. And we made a small calculation, making a few hypotheses here about this chance for the materials to recombine or not. And we were able to show that indeed on fresh material, the chance for the excitant that to remain separated is much better, 87%, than in the case of degraded materials. So we had a way to, at the nanometer scale, identify the fact that this good intermix was helping to get a better, more efficient organic solar cell. And this is ending my presentation. Now I guess we have time for questions.
Yes, thank you very much, Peter and Pierre, for these very exciting presentations. This is Thomas Müller here speaking, Director of Development Applications at Bruker. I'll be hosting the questions. I see some of you have already submitted questions. You can submit them to the questions dialog box. Give me just a moment to get organized, and I will host the questions. If you do leave the webinar in the meantime, please do take the exit survey. We're planning to have a very strong webinar series also next year, and really always benefit from your feedback to pick the most relevant topics, such as the one today. So yeah, let me start going into the question. There was one submitted very early on, I think during Peter's part of the presentation on Peter mentioned the control of both oxygen and water at the 1 ppm level in the glove box. There was a question, any comments on what would be the importance of controlling oxygen content at that level? Peter or Pierre, do you have any comment on that?
I think I can answer that. Yeah, the water concentration is by far the most important in my experience for the electrical measurements. Oxygen concentration has been very important for some other related measurements, like electrochemical measurements on lithium-ion battery type of materials, where oxygen is really taboo. For the electrical measurements itself, like on the semiconductors, I'm assuming now that the oxygen content could stimulate oxidation growth a little more than when it's not present, but I don't think that's a major effect. It's really the water layer that plays a role.
Yeah, thank you for this detailed answer. And in general, we're actually getting a lot of questions in now. So if you have further questions, or if you find you have follow-up questions, you know, we can follow up with email later on also with you. I see a second question. Actually, the second question is regarding KPFM measurement. It's stated here that in KPFM, the measurement is based on a metal-metal interaction. However, when the sample is a semiconductor, one can still obtain a nice image, but can one then trust the measured values? Is KPFM quantitative when you use it on semiconductors? From my side, I would say, well, in KPFM, you measure with a contact potential difference, and it'll be related to a difference in work function. But maybe Peter or Pierre, you have more comments on this, on KPFM for semiconductors?
Yeah, the typical application will be on metal surfaces and less on semiconductors. That's not because it's not possible on semiconductors, but it is because it really measures the work function, which can be strongly influenced by Fermi level pinning. As soon as you take a semiconductor surface and cross-section it, which is typically what we do in these type of samples, you will have some Fermi level pinning. And that pinning will basically mean that you will become much less sensitive to variations in what you're interested in, maybe the carrier concentration or actual work function of the material, because you're dominated by that pinning. Which is why, for carrier profiling, KPFM is rarely used, and the preference usually goes to methods like the capacitance or the resistance methods.
We use, this is Pierre Iben here, we use KPFM on organic, in our case, to complement what we can get with CFM. We use CFM to go to high resolution image, but KPFM is rather nice because, okay, you really do not damage your sample, which is a good point, of course. And also, it's nice to identify the different materials, rather than to go to very nice resolution mapping, but to really identify the materials that you have to assess the kinds of material that you have. For instance, we have some examples which I think will be published soon by Ravi Shintala, which is working on this on our side here at IMEC, where we have been using KPFM to identify PCBM and P3HT before doing CFM mapping.
Okay, thank you. Thanks also, Pierre. Yeah, there's another question here on the system in the glove box. You mentioned a lot of very nice examples on using the SSRM and also conductive AFM modes. What other electrical modes can you actually run on that system in the glove box?
You can use the AFM in its full functionality. So whatever modes your AFM is equipped in, you could execute those in a controlled environment. Probably the question then is, well, which modes will benefit from it? It's more a question towards the samples, I think. If the samples are semiconductor, chances are it can benefit from it. Yeah, it's strongly dependent on sample. So
you may have because you use circulation and pumps and so on. So if you really want to make low noise tapping measurements, for instance, you would prefer or to stop the pumps or to make a measurement in air. It depends. For instance, in our case at IMEC, we have two of these icon systems, one inside the glove box, one which is in air. For tapping high resolution measurements, we still prefer to use the system in air currently.
There's maybe a related question on any tips for reducing noise when putting an SPM in a glove box. I certainly know we did quite a bit of engineering to make that work well. But maybe, Peter, you have additional comments there?
Yeah, I think a lot of it is in the engineering. If at any time there is a noise issue, I think consult with one of our regional applications experts, and they will help you out. I mean, whenever you work in a controlled environment, there's quite a bit of cables that go in and out of that, so we need to make sure that those are properly decoupling noise and yeah, those type of concerns.
Yeah, be it for high force measurements like SSRM or for the other modes where we typically use no peak force modes, so intermittent contact modes, typically we very rarely use tips with very low spring constants. So I guess that's a good point also about the peak force. You are using tips with a relatively high spring constant, so you do not suffer too much from this.
Thank you. Thanks. Here a question, it's noted as a question for Pierre. Can you comment on measuring the resolution of the technique versus, the resolution of the tip? Which one would you say it is?
I'm not sure I do understand. What I told you is that the radius of the curvature of the tip is much larger than the spatial resolution that you can get. That's the first comment. For the rest, Resolution, I did not go into detail on that, it was long enough, but resolution when you measure carriers, it's not a straightforward concept. It's not like just optical resolution. There is what we call the spatial resolution, which is somehow the smallest features you can measure. Another very important one is the dopant gradient resolution. Are you able to measure very close to each other very different concentration of dopants, of active dopants? And this will be, for instance, related to the bias that you are using, stuff like that. So, yeah, I'm not sure I'm answering the question, but just to say that resolution is not such an easy thing to describe.
Yeah.
Do I answer the question?
I think maybe we can follow up if there is more on that. Yeah, there a number of questions are coming in on the solar cells. There's one here on a customer who's measuring P3HT ICBA solar cells, wants to measure photocurrent and has an issue with moving the material around during the measurements when doing either conductive AFM or TUNA using SCM-PIT type tips. Any advice on that?
Yeah, Thomas, although I did not do the measurements Pierre presented, I can comment on this. Yeah, I mean, once we move to organic material, often material is quite a bit softer. So if we still stick to the same mode, contact mode, and forces that we use on the semiconductor, yeah, we will definitely be rubbing things apart. So we need to be careful about our force and cantilever selections to operate in low force mode, or preferably use an alternative to contact mode like this peak force TUNA mode, which allows to control that normal force to much lower forces and eliminate the lateral force. And when using that, there will be no dragging, no lateral dragging of the sample.
Thanks. Yeah, and maybe related to that, any hints on particular probes to use when investigating these samples?
Personally, I've used a variety of probes. I mean, personally, I like to use the silicide, platinum silicide probes. And then depending if we use contact or the peak force mode, we need to select the proper spring constant. In contact, probably a little bit softer than in peak force tapping.
Yeah, let's see, maybe one more here on the organic solar cells, PCBM, P3HT. How can you distinguish them by KPFM? And maybe we can follow up there later if there's any literature on that, but any quick comments on a KPFM on PCBM, P3HT?
They have different work functions.
Yeah, okay, that's what I thought also, yeah. Here's a question, how does the FIP processing affect the doping profiles? It's known that the gallium contamination may twist the doping profile in SSRM experiments. Any comments on that?
Yeah, we had to work quite a bit before we could get this properly done. Basically, with the procedure as we do, we expect to have some contamination over 2, 3, 4 nanometers in depth, not more than that. So meaning that after 1 or 2 scans, basically we remove this layer that has been contaminated. So I told you, every scan in SSRM will remove a few nanometers of material. So basically we are able now to get some surfaces where after 1 scan, or even the first scan when you go at higher pressure, we are on a surface which is no more contaminated with gallium. So it's not that we are avoiding completely the gallium, it's just by the lapping, by really the small angle, by the lowering of the energy, we are able to reduce the penetration of gallium really to a few nanometers.
Thank you. Here is, let me maybe do one more. I think we're running way over time, so we may stop soon with the questions, but follow up later. Here's one on resolution. I think this will follow up on the earlier resolution tip versus technique question, referring specifically to where you mentioned that 0.3 to 0.5 nanometer resolution is attainable in a sense. Can you comment on that more? Is this tip limited, or could the technique even be pushed further than this?
So the first point is, I should say, is that typically when we see this peak, we can see an increase of the peak of the resistance over a thickness of oxide which is 0.3 to 0.5 means the resolution is 2 times that. That's the first point. As you can see in the slide, the resolution is 0.6 to 1. That's 2 times this. Yes, it is tip dependent. It is going to be also a bit voltage dependent, and it is going to be force dependent mainly. Yeah? So these kinds of resolution you can reach only if you use small voltages, 50, 100 millivolts. If you are using very sharp tips that are not presenting any double tip contact, so meaning also measuring in low humidity conditions. And you can get only if you measure on a very nicely prepared and flat surface, and also not to make a scan about 10 microns, but a small scan size. So clearly I want to say that these kinds of resolution, this is in ideal conditions that you can reach them. But if you are in ideal conditions, you can reach them. I think if you look in the image that I presented, look back in the image that I presented today, you will see some of them where we can see the gate oxides, or we can see very small features present in the image. So we can really, in reality, reach this resolution around 1 nanometer. That's sure. But not with all tips. You need to really, and not with all kind of sample preparation. You need a very flat, nicely prepared sample, and you need to select a tip, very sharp tip, that you can use at a moderate force.
Thank you. Yeah, thanks, Peter, for explaining this more carefully. It seems actually a number of users were really wondering about this question of spatial resolution, understanding that. Unfortunately, we're running out of time. I see there's actually one question asking here explicitly, where can one find a copy of the presentations? The answer is we will post them online in the webinar section of the AFM part of the Bruker webpage. And you will also receive an email with this particular link following up to this webinar. And with that, I want to thank everybody again for attending today. Please do take the time to take that very brief exit survey. We really value your feedback and want to know what's more relevant, most relevant really for you for future webinars. Thank you. Bye-bye.
Thank you. Bye.